once again, welcome to an INB382 demonstration video. This one is about ray tracing, or a very simplified form of ray tracing. So I'll fire it up, and this demo is effectively a procedural texture. So we have a quad with a very simple scene, all processing away with 3 spheres, 2 smaller spheres sitting on a very large one, all of them reflective. So I move back to the editing area. You can see that we can turn this around to the side, and this is a procedural texture. So for those who did for the previous lecture on procedural texturing, this is an interesting form of procedural texturing because you're synthesizing an image as a texture on the surface of a polygon. And you're allowed to do that because we've got GPUs. But it just makes it an interesting concept because here we have an image precise algorithm. And you can see we can push ourselves into the scene, and we have effectively very little aliasing occurring, except maybe at the bottom of the scene. But again, it's a bit hard for me to move around. I probably can't do that. I can do this. Yeah, that's better. So the aliasing, of course, is that image precision. So this procedural texture does not anti-alias. Does not alias when you bring it closer. However, keeping that in mind, this takes a fair bit of processing power. So we're looking at effectively using a GPU as a ray tracer, a very simple ray tracer, not very general, with a few effects such as reflections and shadows. That's about it. And this is all done in CG Shader Model 3. So I hacked this from an NVIDIA demo from the CG browser. And therefore what you'll find is that this is very restricted, but it gives you some insight into some image precise rendering using the GPU. So it's a nice sort of thought about, well, how can I do this? Going back to, so if we look at the ray tracing script, we pass in the camera to world matrix because we need this for some transforms with the rays, because we've got to actually transform to the correct camera model for the scene from the camera model with the values coming in. So it's all good. Going to the shader, this is a very complex shader. As you can see, how many lines of code we got here? It's about 276 lines of code. So this started pushing the limits of what the Shader Model 3 would let me do on a Mac. And I found so compared to the NVIDIA version, I had to hack some parts away, but still it's viable and shows you a scene working. So it should run on Macs and Windows. Haven't had any complaints from students yet, but there's some vagaries around this. So first of all, I'm not going to go into huge amounts of detail in this video. Look at the code yourself, because in the end, for this unit, I only teach the theory around ray tracing and concepts and sort of its usefulness. I don't go deeply into it because it's not really used in real-time graphics much. But this at least gives an intro of sort of how you might attempt it using shaders. Of course, the better way to do it is to use CUDA or OpenCL. So some sort of generalized, so GPU languages are much better for this, because of course you need scatter and gather operations, because effectively you fire a ray into the scene and it could hit anywhere in the scene. Therefore you must interrogate a database of the scene efficiently. And that's a bit of a problem for GPUs, because they are an object-space design system which usually discards any global information about the scene. But it doesn't matter. We can play around here. So I will take you down to here. First of all, here's our database. So we've got a static set of array of structs, and we can see here that we have set up, I haven't particularly documented it well, but we've got the requirements for, I think, the center, and I think the color of the sphere, its radius, and a few other attributes that are used in calculations for sphere intercepts. Of course, because it's an exact operation, we have a bit of an error epsilon as far as determining how close we are to any intercepts. And funnily enough, I couldn't use an array of structs in CG for some of the operations, so I had to create this function which, instead of returning just object index, I had to pass it back as a temporary variable from this function. That was a strange thing, but the compiler did not like it. So if I didn't dig too deep, but some of my programming here is a bit odd because I had to modify it to suit what the Unity version of CG would allow. Here's our sphere intersect function, which is sort of the major component of the work that happens. It's based upon the lecture notes, so it's all straightforward. Generation of a sphere normal, just create them on the fly by taking the difference between the point and the center of the sphere, so that's all good. Then we have a nearest hit. This is useful for shadows and so forth and so on, reflections. Then we have a test for any hit. So this is a quick decision on whether something has actually been hit in the scene. Our Phong shading, which is calculated here. So once we have the vertices, shininess, and the eye vector, we're able to put that together in a typical Phong shading pattern and spit out the color. Sorry, Phong lighting model and spit out the color. It's Phong shaded because we're ray tracing the image space. So it's all good. And this function here simply is able to enable us to spit out from our Phong values some other shadow factors as well. So enables us to mix it together. So shadow equals any hit shadow ray, blah, blah, blah. But keep on going down. So the vertex shader, very simple because it's sitting on a quad. So we're not doing much with the vertices. It's all done in the pixel shader. So all the intersections are done in the pixel shader database. The vertex shader is practically empty. We just make sure the quad doesn't disappear and the texture coordinates are transmitted as pass-through to the pixel shader. A very simple scene animation, just hand modification, so to speak, of the array of values. So here we're just moving it around in a circle. One of the spheres rotates. And then all the work is done, of course, in the pixel shader. So for any pixel that's been generated, first of all, update the scene. So in effect, this contains a tiny scene graph to play with. Then we calculate our eye ray. Then we transform it by the mu matrix that we have passed in. And then we're looking for the nearest hit from our database of objects. So we pass in, and actually it does it in a hard-coded manner. So the nearest hit up here just uses the myObjects that uses this function, which uses these objects here and contained inside the database. So it's all done as a hard-coded function for this very simplistic scene. If there's a hit, well, we can shade the surface. So we can say, all right, at that point, the first hit of the ray on the surface contains this color. And then we go, right, but there might be a reflection contribution from another object in the scene. So we use the reflect function in CG around that ray, around the normal, generate this reflection ray, and then check if that hits something in the scene. If it does hit something in the scene, calculate a normal for that hit object, and then shade that hit object so we can add that color to the color of our sphere. So this is how we get, as you can see here. So you can imagine we're hitting the sphere on the surface here, the blue sphere, and when we reflect that ray around the normal, it's hitting the big sphere down here. So that means the bottom sphere has to contribute some color to the surface of this blue sphere. So this is how we create our reflection. Very simple reflection model, and it's only one bounce. So as you can see, it doesn't loop through anything. It just simply goes, okay, have I hit something else in the scene? Well, I better account for that. And that's fine. We don't have transparent objects, so we can't propagate rays through transparent objects in the scene to check for other hits. All right, so that's a reflection ray. So if we don't hit anything, just add the background color, so it's a bit of blending of the background color to the scene. If we don't get a hit at all, then we just have the background color in the scene. So as you can see there, if we don't hit any of the spheres in front of us through the pixels, we just get black. And that's all fine, so that's the background color. And so this happens for every pixel in the scene. So this ray trace function is happening every pixel in the scene, but it's implementing ray tracing. It's not implementing a typical shading model, excuse me, that might be used for your surface representations for object space rendering in games. And so what this gives us is a very simple looking ray tracer, and that's quite useful as an exercise. I would not recommend that this would be the way you would do ray trace scenes in a real game. That's a very complex concept. You can look at all the sort of brigade style renderers out there using path tracing on the latest GPUs to provide very accurate physically based rendering in near real time. But this is just a nice example for, as a student exercise for understanding the use of ray tracing and how that may be integrated with a GPU system. Okay, thank you very much.